Thank you very much for the introduction. Indeed, my topic today is network automation and network autonomy at pace and scale, and describing the most important stepping stones to get to an autonomous network operation. Zero-touch networking or autonomous network operation is a cool concept. It triggers and challenges our mind of getting to that state. However, we should not forget that why we're actually doing this is due to our customers. We have an ambition and a goal to continuously improve the customer experience. This sometimes may increase complexity in our technologies, and certainly in a modern networking world, complexity is always present. That puts a lot of challenges to us. Zero defects means that whatever change you do to the network cannot cause an error or degradation in quality. And clearly, if you have no errors, you have no defects. That should be the case. Our ultimate aim here really is to get to a state of zero complaints, where technology is not a root cause for a customer's complaint. And I think these 3Cs or 3C networking is a great ambition to have for us as technologists. So what are the three, in my opinion, most important elements when we look at zero touch? I have network management, network optimization, and user experience management. These three elements are crucial, are elements of achieving zero defects and zero complaints, and of course should be an integral part of a zero touch strategy. I'm not going to read everything you have on here. I think it's fairly self-explanatory. I would mention here that for me, anomaly detection is a very, very crucial element and enabler for the zero touch. It is something that needs to be built in as we go towards autonomous network operation, as it allows us to capture events and issues in the network before they become critical incidents that would impact our customers' quality. So absolutely crucial. Our telco networks produce huge amount of data continuously. It comes from the control plane, from the network elements, from the various layers in the telco stack. It comes, of course, also from the user plane, the generated data by our customers. Now, this is big data. We have very high volumes of data. We have a very high velocity. As you see the example here on this page, you have 1 billion raw events per day or 30 plus events per milliseconds, possibly an alarm per second. A lot of duplications in those alarms, as the alarm will continue until you resolve the problem that caused the alarm. You have large variety of data, unstructured, ASCII, hex, binary, HTML, you name it. And of course, timing is so essential and crucial for much of this data and how you actually deal with that. So the event process, the definition of what you do with this data becomes even more important. So yes, telco is also very much big data, and how we deal with those challenges in there are very much also a big data challenge. When you're having billions of raw events generated per day, 50 plus per millisecond, one alarm per second, you're having lots of unstructured data flowing through the network, generated each network element, not to talk about the user-generated traffic and data that also goes on, in particular on the user plane as opposed to the control plane. Very clearly, not all of that is equally important, and certainly not equally important when the aim is to provide, let's say, enablers for zero touch. So this is just a very quick and a little bit provocative example of no, not all data is gold. No, big data in a telco sense is not new oil. There are gold in there, but even the gold actually often decays and it becomes part of the pile of dung that is generated every day in a telco network. I think it's always good to remember that automation and autonomy are not the same. While automation may be part of autonomy, autonomy is much more. Automation, humans remain very essential and involved in the process, while when we talk about autonomy, we have built in cognitive solutions that largely takes the human out of the equation. So keep that in mind as we go forward. So if you look at where we are today, we are really very early in the process and the path to zero touch. We are largely tool assistant driven. We are not completely manual. We are not back at the days of everything happening via a command line interface. So we are getting a bit more advanced. We are adding some cognitive solutions across the stack, if we are brave enough. But largely where we're moving towards, at least the next coming years, is towards a framework that is as close as possible and as realistic to a cloud native environment. I think this is where our aim should be and focus should be, is to get to a telco cloud native environment that is designed and optimized for our telco stack. Of course, beyond that, where we go to autonomous operation, where humans are no longer involved, or at least very little involved, particularly as you go to the full sort of visionary zero touch, level 5, if you want to call it that, sort of the highest level of autonomy, then we're still very much far away from that. I think that's always good to keep in mind. Today, we strive towards that, but the focus really is on a telco cloud native, which doesn't necessarily involve AI and machine learning, but simply reusing the cloud native framework, automation framework that we already have today, working very well in many, let's say, IT driven environments. One of the topics that I've been very much engaged in over the last years has been, as you build in more cognition, more intelligence into the telco stack, particularly driven by enabling higher degree of autonomy, is how do you orchestrate that? How do you control that? And at least one of my critique points of the present thinking, a lot of the present thinking has been that it's very much driven by our own anatomy. It's driven by a very centralized view of control and orchestration that basically goes from top to bottom. Now, if you look at our own anatomy, it's not a surprise that if you look at the nervous system and the control, there is very little autonomous intelligence there. Also, it certainly has not been designed for redundancy. Most of our networks, the classical network, telco network, even most of the more and more modern ones, have not been designed for a lot of redundancy. And in terms of anomaly detection, is rather either missing or very unsophisticated. And I'm not sure that as we go into the future and actually talks about autonomous network and autonomous network operation, that this would be the right architectural framework to think about. On the previous slide, we discussed the sort of fairly prevalent view of centralized control and orchestration, very much taken from our own human anatomy with a single brain and a very hierarchical way of controlling the human body. I personally believe that that is not the right way to think about a modern network, in particular not as we move towards autonomous network operation. I think the right inspiration to take from the natural world could possibly be the giant Pacific octopus with 9 brains and 3 hearts. Clearly, if we could build something like that into our telco stack, we would achieve a much higher degree of autonomy between the parts, which I don't find problematic. And also obviously a much higher redundant, high available system design than what we today have, where we still are very much sensitive to that central brain and its functioning and possible not functioning. So while anomaly detection, even in this sense from the giant octopus, is not very sophisticated, it also becomes much less critical, exactly due to its very high degree of redundancy and autonomy between the parts. So I think when we think about the architecture, the modern architecture, we should certainly rather use that as an inspiration rather than the human anatomy. And by the way, I'm not saying that you can completely get away from having some kind of centralized orchestration and control. I think you will always need that, but you should build much more autonomy and intelligence into the layers, particularly as we move towards the future. So let's move to the network view. This picture shows you a telco stack. It shows the traditional layers you would have in our telco network, being it either mobile or a fixed network traditionally. It shows you from the end user device all the way up to the core switching, the data center cloud, and possibly even to a back-end data center or an OTT residing on the public internet. It gives you a bit of an idea about where you traditionally would find big data processors, big data store, as well as where a particular intelligent agent or machine learning app may be integrated into your telco stack. What I've tried to depict here is also in a closed loop application in the access layer, which could be self-optimized RAN, it could be any other kind of closed loop optimization that you may apply, in particular in the RAN, but of course could apply this in any part of the network. In this particular example, the closed loop optimization is actually making use of higher level information and possibly also interacting with other intelligent agents residing in different parts of the telco stack. So that gives you a kind of idea about the complexity and often use case specific implementations of big data, as well as actually the intelligent agent and machine learning app. Typically also, as you move up northbound, you actually will find more and more computational resources available. And if you look at the big, let's say, training of models or highly complex computation, simply would actually end up happening in the data center. Although as we start discussing edge cloud, where you also would have significant computational resources available, I think also in terms of model sophistication, you could actually also easily imagine that a lot of training possibly could happen there if this if your application is making use of that. So in the previous slide, we saw how AI agents or machine learning agents could be distributed across the telco stack. We saw possible feedback loops between agents in the various stacks. We saw also the importance here on closed loop operation, which is a very essential point for the autonomous network, or creating a very high degree of autonomy, at least in some areas of your telco stack. But it doesn't come without problems, right? There are some challenges, particularly as you start looking at implementing machine learning and intelligent agents in a fairly complex industrial setting. And I just here want to give you at least three, I think, very concerning topics that you certainly should consider when you're looking at the overall software architecture of your implementation. One is entanglement. So what is entanglement? Entanglement basically is that the various systems that you have implemented and deployed across your telco stack, they interact with each other, they mix signals or data between them that is not necessarily confined to that individual layer where you implemented your agent. And that can be problematic because it becomes very difficult to understand what each individual agent is doing, in particular in terms of troubleshooting and isolating agents in order to improve them. So that's one thing, and I think that this is certainly very concerning, particularly if you have agents that are working on different aspects of different closed loops, that one, for example, optimizing your network, and the other one optimizing, for example, the customer experience, which could be in certain areas quite different in terms of action. So worth definitely to consider, and also really look that you got that right. Correction cascades is very simple, that as you have several agents with different functionalities or sometimes fairly similar functionalities, it becomes very difficult to just optimize one and still overall have an improvement of your systems. And this typically is what you call correction cascades, where while one part of the system is being improved, the overall system either doesn't improve or actually deteriorates. The last but not least is an undeclared consumer. What's that? That basically means that while you have a known agent that is producing an output in your software architecture or in your system, you're having other entities that is using this, but you don't know about it, or it's not been declared, it's not been publicized in general. And this can create some very nasty feedback loops that also is worthwhile keeping an eye out for. So just to give you an idea that while we would love autonomy and we have this idea that implementing intelligent agents across the telco stack for various functionalities, that it also is, there are certainly certain software architecture or software engineering issues that you should consider. So what does all this mean? I mean, I think in general, let's just be open about it. And I think that's quite important, right? That we have very little experience with integrating advanced machine learning into an industrial scale complex system, such as a telco network. Most of the works are fairly isolated. It is very narrow in how a machine learning agent interacts with the rest of the system, and it often confined to either one or very few agents. And usually these agents are working in conjunction with each other and might not necessarily have, let's say, different different functionalities or different intent. So just keep in mind. Now, the good news is, of course, that there are a lot of fora that is already looking at this. There is a huge industry attention to this topic, as you see on the slide here. So we are certainly progressing in the right direction on getting, let's say, more experience and more data on how to actually do this in a complex system such as a telco network. Just to give you this kind of idea of the complexity we're talking about. So this slide actually shows you sort of in an illustrative way how you actually would like to deal with a closed loop optimization or a closed loop setting. You have learning agents or AI controllers or ML controllers, whatever you like to call it. You have an environment. This usually resides in your data center, in your cloud, and actually looks at the overall, let's say, quality and experience of the network, as well as, of course, on the customer experience. And you have a loop here, and of course, you can iterate on this experience in terms of quite a few iterations per relevant time unit, sometimes thousands of iterations on a per second basis or per minute basis. And of course, the cool thing about this compared to the typical manual way is that you really are optimizing both the network quality as well as the customer experience pretty much in real time. Typically, we call this reinforcement learning. It's a closed loop. It's very dynamic, and this is all good, right? But what is so essential in this architecture is, again, and I've stressed this many times, is really the anomaly detection, because you need something in there in this loop that is able to break the loop in a situation where things either become unstable, which is certainly a possibility, particularly if you have many different agents that all have their own closed loop or interaction or particular intent that might counteract another agent. So having anomaly detection really embedded into your architecture, I cannot stress enough how important that really is. Here at the end of my presentation, I would like to give you some examples that I believe is worthwhile considering. Let's not forget that we do this in order to quantum leap our customers' experience as our network architecture design becoming increasingly complex. So when we take a look at the examples I have on this page, I think chatbots in general are no regret moves. You need to keep it simple. There still is a lot we have to learn about how our customers and also professionals interact with bots. And there's some very interesting work being done currently in Israel to look at those aspects. And I have given you a reference on this page. RPA, robotic process automation, no regret move, good return on investment, both in business operation as well as network operation. Going into the next generation of RPA, intelligent automation, where we add cognitive solutions to the RPA, AI, machine learning, I think are very interesting and certainly a very logical evolution of the classical RPA. Specialistic or narrow AI, something that again in general are no regret moves. It has a short-term return on investment, and it gives us a lot of experience with how to integrate intelligent agents into our telco stack. Industrial scale AI, well, that's what most of my presentation today has been about. it is complex, but we also need to get this under our nails. We need to understand how to integrate this into a complex setting such as our Telco Stack. So we are on that journey already. Anomaly detection, no surprise. I think this is one of the most essential elements of the whole story. Get that in, start getting experience with it. And I think in general, in my opinion, this is an easy return on investment. So with that, I would like to thank you for your attention. I wish you all a great day. Take care, stay healthy,